Alright gang, here we go. So this is Chem 2 Unit 5. We're going to be talking about ionic bonding, lattice energies. We're going to dispel one of the biggest sneezing trees of all sneezing trees in Chem 1. Alright, so this unit we're going to cover basics of chemical bonding, and then after this, so we're going to do chapters 8 and 9. Okay, and so first up, we're talking about different types of chemical bonds. Alright, so there's three basic types of bonds in chemistry. There's ionic, covalent, and metallic bonds. We're going to focus today just on ionic bonds, okay? So ionic bonds are really electrostatic attraction between ions. So when you see this word electrostatic, you should really just think static electricity, right? And like, you know, everybody's played with a balloon and rubbed it on their head and then stuck it to the wall and it sticks to the wall. So that's really just static electricity at work. You're putting electrons on something else. Okay, so you can kind of imagine it almost like magnets, right? So we're going to use sodium chloride, NaCl, a lot in this video just as our basic example. And so these two, because the sodium is positive and the chlorine is negative, they're opposites, so they attract each other, and so they kind of do this number and kind of attract each other. So that's really what we're talking about. All right, covalent bonds are sharing of electrons. All right, and we'll talk about why that happens, how that happens later. And then metallic bonds, okay, are free electron clouds, or a sea of electron is how they're referred to most often. So this is a sea of electrons. And they kind of hold the atoms together for the different metals, right? So anyway, so we're going to focus on ionic compounds. But first, we need to talk about Lewis symbols. All right, so this idea of Lewis symbols. So this guy G.N. Lewis, a brilliant chemist that came up with lots of important ideas in chemistry that high school and early college chemists learn about. Anyway, so he developed a method to help us keep track of the important electrons. And you should know by now that that chemical reactions occur between valence electrons. Okay, and so really, if we can keep track of the number of valence electrons, then we're better off in being able to predict what's going to be going on in our reaction. All right, so he used this thing and he called them the Lewis dot structures. And essentially, it's just the name of the element and then a dot around it representing each of the valence electrons. Okay, so here we've got group 1A, and group 1A has one valence electron, so it gets one dot. The 2A's have two valence electrons, so they get two dots. And 3A, 3, 4A, 4, etc., until eventually you get to the noble gas where you have 8. All right. Now, when forming compounds, and then so this right here is an important rule that we focused on a lot in Chem 1, but it's actually kind of a sneezing tree. Not kind of, it's one of the biggest sneezing trees in all of Chem 1. All right, so atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons, and this is a lot of time referred to as the octet rule. Now, the problem with this is it's not actually, and you probably have already realized that there's a lot of exceptions to the octet rule. And that's because it's not really much of a rule. It's more like a guideline. Okay. Anyway, so we're going to talk about why do elements actually form ionic bonds today. And then tomorrow, in the next video, we'll actually talk about why molecular compounds form bonds. Okay. So first of all, ionic bonding always occurs between a metal and a non-metal. Okay. All right, except for group A, because these are the noble gases and they don't really bond. All right, so metals and non-metals. All right, and they involve electron transfer. So one of them gives up the electrons to the other one, and they're always very exothermic reactions when you form an ionic compound. So for example, if we had a container of chlorine gas for some reason and put in some sodium metal, both of these things pretty reactive all in and of themselves. You dump that in there, close it up, and then the electron transfer will automatically happen. We have a redox reaction where the chlorine and the sodium will come together and you'll get a big nice fireball, and you'll get to form some sodium chloride or NaCl salt as your product. Okay, so so you've probably, when you were in Chem 1, probably saw this thing almost verbatim, right? So you got sodium, it's got one valence electron, chlorine's got 7, and the sodium gives up its electron to chlorine, right? And then you get the sodium ion, and now it's plus because it's got one more proton than electrons that it had, and chlorine has one more electrons than the protons it has, so now it's negatively charged, right? This should be old hat for you, okay? Now, the reason this occurs is because one element gives up an electron very easily. Okay, that element in this case is sodium. It has low ionization energy. So remember, ionization energy is the energy it requires to remove an electron, right? The energy required to remove an electron. Now notice that we're starting to talk about energy, okay? This is very important because this is actually going to help us dispel that sneezing tree that we talked about earlier. All right, the other element will readily gain an electron, and it has high electron affinity. Now, remember, electron affinity is defined as the ability to give energy for electrons. Okay, so this is essentially like the chlorine in this case is just a really rich guy. He's got a lot of extra energy. Sodium really would like to trade his electron for energy. Okay, and so the chlorine will trade energy for the sodium's electron. And so notice that we're starting to zero in here on this idea of keeping track of the energy required in order to make our compound. Okay, and so these arrows are indicating the transfer of that electron. Okay, here's some properties of ionic substances. Okay, they always have well-defined 3D structures. So you've got sodium chloride. All right, and the chlorines are the green ones, sodium's the purple ones. All right, and notice that they kind of surround themselves with 6 versions of, or 6 ions of the opposite charge, right? And so they've arranged themselves in this nice little crystalline structure. Okay, they're usually very brittle. They have high melting points. Okay, this ionic attraction, this ionic nuclear or ionic intermolecular force is very, very strong, so it's hard to break. Okay, they're crystalline, okay, and then they cleave along smooth lines. So if you break a sodium chloride crystal, you'll usually get a nice smooth line right along the edge of this crystal structure. Now here's where the rubber meets the road. All right, now before we get to energies, I just want to take a moment and make you picture something. I want you to think about this real quick. All right, if you were on a roller coaster, say you're on a roller coaster that's starting up here, okay, and it goes down like this, and then the roller coaster comes up somewhere like this, right? And so you're sitting here on the roller coaster, and then you're sitting right here about to go over the edge when all of a sudden the power goes out on the roller coaster, right? And so you're stuck here, and then somebody jerks your cart forward, and just barely you teeter over the edge. Okay, now if you're familiar with physics, you recognize that up here at the top of the peak, you have a whole lot of potential energy, right? And then as you go down the hill, you're going to be converting that potential energy to kinetic energies until you have only kinetic energy at the top of the hill, and then you'll be back here and you'll have only potential energy here at the top. Now, our roller coaster is going to come down here, right? And it's going to travel down here. Now, the whole way, because this is a real roller coaster, we have friction. And so some of this potential energy is going to get lost to heat. And so you're going to get up to the kinetic energy. And since this side is just as high, you're not going to make it up to the hill. And then you're going to come back this way. And then you're going to come in, and you're not going to make it as high as you were. And you're just going to kind of keep doing this until eventually you are stuck in your cart at the bottom of the hill. And you came to the stop at the bottom of the hill because this is the spot of lowest energy. Okay. All right. So keep that in mind. Okay. So the reasoning is that when you're having any sort of chemical reaction, a lot of times the chemical reaction takes place spontaneously, purely because it's energetically favorable, meaning the energy state that it ends at is lower than the way it started. So just like our roller coaster here, the cart doesn't like to be at the top of the hill because it has a lot of energy. So one little jerk got you started, and then eventually you ended up at the bottom of the hill at rest. Okay, same sort of idea here. So notice that the general energy trends here, so these are right here, this energy level right here, okay, is exactly where we started. Okay, this is where our elements are when they're by themselves. We got sodium metal and chlorine gas, and they're kind of at this energy level. Now, this isn't exact, but it's kind of a great way to look at it, okay? And then down here, we've got NaCl. Now, notice that it is at a lower energy than the Na and the Cl2 separately. Okay, so right there, you should know that sodium chloride is energetically favorable. Okay, so that's really the real reason that we form this ionic compound, is because it's energetically favorable. It doesn't really have anything to do with that octet rule, although that's a good indication that it's energetically favorable. But really, the real reason is because it's at a lower energy, so it's more stable. Okay, so with this cycle, it's called the Born-Haber cycle, we're able to calculate exactly how much energy we get from making an ionic compound. So this is a very important cycle that you need to understand. So if we start with sodium solid and chlorine gas, okay, so if we were going to make sodium chloride, let's just write out our reaction here. So we're going to start with these guys at their elemental state. So that means our sodium is solid, chlorine is a gas, and then we make NaCl. That is also solid, right? This is our elemental states for sodium and chlorine. And then we'll go ahead and balance this guy. So we need 2 of those, and so then we need 2 of those. All right. So now we've got this balanced chemical reaction. Okay. Now when we're defining it, our reaction is always going to be in kilojoules per mole. Okay, and because of that per mole, we're going to be defining it based on moles of our product, and right now we have 2, so we're just going to divide everything by 2, and so that's why down here we have Na solid plus 1/2 of the chlorine, because we only need 1/2 of that Cl2, right, to make the NaCl. All right, so anyway, so that 1/2 chlorine, that's the key. Anyway, so we have this guy here, so sodium and 1/2 of a chlorine gas. All right. And then all we do from there is we're just going to convert them into gases. All right, so each of these steps is we're putting in a little bit of energy to help turn them into their gas forms. So we first put in a little bit of energy to turn sodium into its gas form. So there's the energy of formation, or the enthalpy of formation of sodium into its gas form. And then we're going to convert chlorine into its singular element, right? This is kind of what it needs to look like in order to start forming our ions. Then we have to expend energy to make this, to use the ionization to meet that requirement, the ionization energy of sodium, right? So we add in a little bit of energy to make it into the ionization energy, becomes Na+, and then this electron is now free. Chlorine will expend energy or lose and become more stable. See, that's what it means by expending energy. It's going to become more stable by giving off its electron affinity energy. Okay, in order to become sodium plus and chlorine gas, and then these 2 will combine together and we get NaCl. All right, so that's called the Born-Haber process. And then by using this process, okay, we can use something that we'll talk about later called Hess's law. Okay, and based on Hess's law, we can just add these all up, and we'll end up with what is called the lattice energy of whatever it is we're talking about. All right, so there's lots of things that kind of that affect it. Okay, so there's the ionization energy and the electron affinity. Okay, but really it's kind of comes down into these steps. So it takes energy to convert elements to their atoms, and this would be an endothermic reaction, right? Here our reaction had to go up, right? We had to add in energy in order to turn them into our elements. Then we had to add energy to make the cation. This was endothermic, right? And that's this step when we put in energy to meet the ionization energy of the sodium. Then we release energy in an exothermic reaction by making the anion. That's the electron affinity energy that's released when our chlorine becomes chloride anion. Okay, and then finally we release a huge amount of energy when we make the solid. Okay, and because these 2 huge amounts, these 2 exothermics, are so much bigger than the endothermics, formation of salts from their elements is a hugely exothermic process. All right. So then we get this idea. Notice that here they talk about this idea of the lattice energy of NaCl. Now notice that they got a negative sign on there. That's kind of an important idea. All right, in the negative height. All right, so the lattice energy is defined thusly. It's the energy required to completely separate 1 mole of a solid ionic compound into its gaseous ions. All right, 1 mole of a solid ionic compound into its gaseous ion. So we're starting with the solid ionic compound and we're converting it into its gaseous ion. So here, these are the gaseous ions, right? They're ions and they're gases, and then there's our lattice energy. But notice that it's defined as converting this into this. So that's why we've defined it as negative right there. All right, and so that amount of energy is released to make the ionic compound in the Bohr-Haber cycle. Okay, and specifically the case of sodium chloride, the lattice energy is defined as a positive 788 kilojoules per mole. All right, 788 kilojoules. Now notice it's positive. That's because it's an endothermic process to turn it into its native ions. Okay, so here's a table of a bunch of different lattice energies. All right, so you can pause and take note of a couple of things. One thing to notice is you'll start to see some patterns that if you're just looking between lithium fluoride, lithium chloride, lithium iodide, you notice that the lattice energies go down with each step. Right, you go from 1030 to 834 to 730, okay? And that's really occurring as this anion gets bigger, because really the only difference between these three things is that anion, that halogen, is getting bigger. And then you can kind of see that same thing occurring here. Here's sodium fluoride, sodium chloride, sodium bromide, sodium iodide. It goes from 910 down to 682, kind of following this pattern. Okay, so lattice energies, we can actually use these patterns to help us predict some things, okay? And we get trends in our lattice energy, okay? So these are the two things. So you physics types will notice this reaction, or this equation here, is very, very close to Coulombs Law, right? So it says that the energy of the lattice energy, or the lattice energy, and I don't know why it's called EL for lattice energy. It's probably some French thing, but I don't know for sure, is equal to kappa, that's a constant, times Q1 times Q2. Those two values are charges, okay? Capital Q's are charges. So this is the charge on 1 times the charge of 2 over the distance between them squared. All right, so that's known as Coulombs Law, and we can use this to actually calculate the electron, or the lattice energy, excuse me. All right, but really we're never going to actually, we don't really care that so much about actually calculating it. We do use this formula a couple of times, but really it's more important to be able to predict trends. All right, so a couple of trends we need to pay attention to. As our charge increases, okay, as the charge increases, we get an increasing lattice energy. Okay, and that makes sense because our electron, or I see an EL and I say electron. Our lattice energy is proportional, or directly proportional to the charge. That's the Q1 and the Q2. And it decreases with the size of the ions. That's that D. So as they get farther and farther apart, this denominator will get bigger. So therefore we're dividing by a bigger number. So therefore this whole value will get smaller and our lattice energy will get smaller. All right. So we're going to do some practice problems here. Okay. So without looking at table 8.1, we want to predict the orderings of lattice energy for these ionic compounds. So let's just write down these guys we're looking at. So we've got NaCl, let's see, NaCl, MgO, CSI, and SCN. Okay, so we got to organize these things based off of their lattice energy. So remember, the two things we care about is charge and size. Charge always comes first, so we're going to worry about the charge first. So let's just look at these and try to determine what the charges would be on these ions. Well, sodium would be 1 plus, so we'll just add a 1 plus. Chlorine would be 1 minus. All right, magnesium would be 2 plus, and oxygen would be 2 minus. Cesium would be 1 plus, and iodide would be 1 minus. Scandium, well, that's a transition metal. We can't really define what that's going to be. But nitride right here, this would be 3 minus. So that implies that the scandium is 3 plus. So therefore, the only one that could, the biggest of these charges would have to be this scandium nitride. So we'll put this guy, this has to be our our highest lattice energy. Okay, so that's going to be that guy. So we'll cross that guy out. Next guy here would have to be MgO, because that's the next one. He's got 2. All right. Now, sodium chloride and cesium iodide, right? They're both 1. So we can't look at the charge. We have to look at the distance between them. So we got to think about our trends in ionic sizes. So remember, on our periodic table, atomic radius increases as we go right to left, and as we go, or yeah, right to left and up to down, right? This is our atomic radius trend. And so, so cesium and iodine, okay, cesium is below sodium, so cesium is bigger than sodium. So we'll just kind of jot it in. Sodium is here, chlorine is over here, iodine is down here, and cesium is down here. So because cesium and iodine are both bigger than sodium and chlorine respectively, that means this is going to be bigger. Now remember, based on Coulombs law over here, as our radius gets bigger, or as our distance gets bigger, our ions get bigger, our lattice energy will go down. So therefore, the only option, that means the cesium iodide has to be bigger, so it's going to be weaker or have a lower lattice energy, so then we can have NaCl would be the next, and then cesium iodide. Okay, and so the option would have to be B. Then we could go back to table 8.1 and double check our values, and you can go ahead and do that. All right. Let's do one more here. So which substance do you expect to have the greatest lattice energy? So we're going to look at these charges. So magnesium would be 2+. Fluorine would be, they're 1-, right? Calcium is 2+. Fluorine is 1-, right? And the zirconium would have to be, well, the oxygen is 2- and there's 4, so this would have to be 4+. All right, so I would expect zirconium oxide to have the biggest because it's got the biggest charge. All right, it's got the 4+, 2-. All right. Last little thing here, electron configuration of ions. Now you hopefully remember when we did electron configurations a couple of units ago, where you just, 1s2, 2s2, etc., etc. Now we're going to do electron configuration of ions. So essentially, this is just when you've lost those valence electrons or gained additional valence electrons. All right, so an easy one to look at. So if we were going to do aluminum and we were just going to look at the noble gas configuration of aluminum, that would be the bracket neon, right? And then it would be 3s2, 3p1, right? That would be the electron configuration of aluminum. Now, if we were going to make this an ion, right, aluminum forms a 3+ ion, right? It's going to lose the 3 valence electrons. Well, these are your 3 valence electrons it's going to lose. So therefore, its ionic electron configuration would be exactly the same as neon, which would be bracket helium, and then 2p or 2s2, 2p6. All right. So anyway, so that's kind of the general idea, is that they're trying to get the same electron configuration as the nearest noble gas. Okay. Pretty easy stuff. Now, one thing that's a little trickier is when you're looking at the transition metals. Okay, transition metals do not follow the octet rule. Really, nothing follows the octet rule, right? Because the octet rule is a sneezing tree. It's all about energies. Okay, but specifically, the transition metals aren't going to gain or lose electrons to try to be like their nearest noble gas. Sometimes they will, but a lot of times it's not going to work right. All right, so the transition metals, when you're losing, they're always going to lose lose electrons because they're metals, right? So they form cations. When they are losing valence electrons, they're always going to lose their valence electrons first. So those are the ones in the highest energy level. Okay, so essentially you're going to be losing the S's first. Okay, then you'll start losing the D's. That's really what it comes down to. Then you'll lose the D electrons necessary to give whatever charge it is you're looking for. All right. So anyway, well, let's do one real quick. Let's do like scandium. Okay, so scandium normally is bracket, let's see, what's it, argon, and then we get 4s2, 3d1. That's the normal electron configuration for scandium. So if you're going to make scandium 2+, that means it's going to lose 2 electrons. So it'd be bracket argon. Okay, and remember, it's going to lose its valence electrons first. Those are the ones in the highest energy level. So that would be that 4s2. So then it would be just 3d1. All right. So anyway, so that's quite a bit to chew on. Go ahead and do those practice problems. Let me know if you have any questions, and I'll see you on the flip side.